Welcome back. We're continuing the trend, the short-term goal of adding arrays. And to do that, this time we're going to be working on compile time expressions, a constant expression, the C23 constexpr keyword, and also initializers. So we have global variables. We can initialize them. We pass the initializer and we store the initializer in the AST. However, we hit the to-do because CodeGen does nothing with them. Right? It simply ignores the initializer, and it will be like it creates a global that is initialized to 0 instead of a global that is initialized to 42. So we need to fix that by initializing it. In principle, what we could do is when we generate code, we could generate a function that initializes the global. We handled that too. So we could add a function that initializes the global and then call that function before we call main. This is necessary if the initializer can have arbitrary complex code. So for example, we could in principle call the function. We could call a function which can then print stuff and do arbitrary dynamic things. But this isn't the case in C. In C, the initializer of a global has to be a constant expression, so it can be evaluated at compile time. There are two things that we need to do. First, we need to verify that the initializer is a constant expression, and then we can evaluate that at compile time. So it's getting a bit laggy here. Oh, I know it's getting laggy. I'm on the code machine. Okay, so let's check the standard. So we've got the rules for initialization, which state that the initializer of an object with static or thread storage duration, or that is declared constexpr, shall be a constant expression. So a global variable has static storage duration because the storage lives statically throughout the lifetime, so it needs to be a constant expression. And here, syntactically, a constant expression is just a conditional expression. They must not use operators that modify things, so like assignment, increment, and so on, which makes sense. And then here, the constant expression in an initializer shall be or value to one of the following: a named constant, a compound literal constant, arithmetic constant, a null pointer constant, so an address, and then here an address constant, or an address plus or minus an offset. So the first step is to write functions that check for all of those things. And then we can check for those conditions and get an error if they're not met. So let's begin. So the first thing is we've got a named constant. So go to the AST. Wi-Fi apparently isn't good today. So somewhere where we define expressions, we already got is null pointer constant. So let's add rule is named constant. So is named constant. Okay, so a named constant. A named constant is an identifier that evaluates to an enumeration, a predefined constant. So I'm guessing predefined as in in the language predefined, or a constexpr variable. And then also member access into those and recursively. Okay, so we don't have any of those. So we don't have enums, we don't have predefined constant, and we don't have constexpr yet. So currently we don't have any predefined constants, named constant. So no expression is a named constant. That's easy. Okay, so the SSH connection to my device is really bad. Let me just restart. And now my Wi-Fi gets disappear. Ah. Okay. Let's try that again. And that feels better. So name constant. Next up, we've got integer constant expression. So this is something with integer type, and only operands are integer constant, named and constant of integer types, character constant, size of, line of, and then stuff that is casted. Okay. So let's try those. So bool is integer constant. Internet is really laggy today. Okay, so is integer constant. I believe we have to like recursively go ahead. So first of all, it needs to have integer type. So if it isn't integer type, then it can't be an integer constant. So that's easy. And then we need to go over each potential expression and check whether this is a potential integer constant expression. So we need to visit them all. So we need to visit all possible nodes. And check. So we've got the define all the nodes right here, and we need to check all of those. Okay. So we can have a null pointer constant expression, which can't be an integer constant because it's a null pointer. An integer constant expression is an integer constant. That's easy. So we've got various built-in expressions. None of those can be integer constants. So like printing stuff isn't an integer constant expression. Then identifier expression can only be one if it is a named constant, right? Because it has to be like a named constant of integer type. Function call can't be an integer constant. You cannot call a function because C doesn't have constexpr functions. We've got cast expressions. So cast expressions only convert arithmetic types to integer type, and I'm guessing like the argument needs to be like an integer constant itself, I'm guessing. Although in principle, like this could be like a floating point constant. So we could have something like int 3.14, which is then so this could be like an integer constant expression, I'm guessing, because we're converting an arithmetic type to an integer type, and the operand itself. No, I mean, we have a C compiler. So let's just check it out. So in bits, in 3.14. Is that an integer constant expression? Trying as to say it. Let's see. Apparently so. Okay. But then we can't do the type check here. So we can't have the type check. Like, because we can't do something like recursively check whether the operand is an integer constant, because the operand is a floating point constant. And we're then casting to an integer constant. Yeah, right here, floating named. So then we've also got like arithmetic constant expressions. I'm guessing like this is the same thing, except the type. So it seems like an arithmetic constant expression. Let me copy the text. So this is an integer constant expression, and this is an arithmetic constant expression. So integer type, arithmetic type. Operands only have operands that are integer constant. This also includes floating point constant. This one does not. Named and compound literal constant are the same in both. Of arithmetic type, of integer type. Character constants, size of expressions, whose result are integer, right? And a line of expressions, and then we also allow floating names or compound literals that are immediately casted. Cast operator shall only commit arithmetic to integer type. Cast operand except as the part of an operand to type of size of line. Okay, so the only difference between an arithmetic constant expression and an integer constant expression, beside the type, is the additional clause that the casting floating points here are only allowed if they're casted to integer, whereas here they are allowed all the time. So in a way, if I'm interpreting this correctly, an integer constant expression is just an arithmetic constant expression where the final type is an integer. Because this should cover everything. Because we're checking whether the type is an integer, which means we're checking, yeah. And this makes sense. Okay, so let's actually write the function arithmetic constant expression, because then we can do trivial recursion. So is integer constant arithmetic, yeah, arithmetic constant. I mean, this is a constant expression, not just, yeah, I mean, I should, because like there's a difference between an integer constant and an integer constant expression. So it makes sense to differentiate between the two. Okay, so let's implement this one first. So let me get all the stuff in order. Kind, note kind. So these are the expressions that we need to check. And then I've got the text somewhere in here. Okay. So an arithmetic constant expression shall have arithmetic type. Arithmetic type. Okay. Pointer doesn't have arithmetic type, so that's still the same. Cast expression. Arithmetic types, two arithmetic types. So it just means that the operand also has to be an arithmetic constant expression. And this recursion wouldn't be possible with an integer constant expression. Because this would then fail on the type check, even though we're casting. And we don't need to do the type check because we only check the result is an arithmetic type and the operand is checked recursively. Unary expression. So unary operators, right? There are a bunch. So the operand has to be like an arithmetic constant expression. So arithmetic constant expression, the operand, and then we need to disallow certain operators, namely increment, decrement. Right, increment, decrement. So increment and decrement return false. These ones return true. And these one return also false. I mean, I'm guessing like deref is allowed. So address of, we can't reach the case of address of because the result wouldn't be arithmetic type, it would be a pointer. So we don't need to check for that in that case. And the result of a dereference is also not allowed because the operand will have. So who does not have arithmetic type, so can't be an arithmetic constant expression. Star foo, for star foo, the operand does not have arithmetic type, so it can't be an arithmetic constant expression. Okay. These ones are explicitly called out in the standard. Okay, I'm guessing that's okay. Next up, we've got the binary arithmetic expressions. And I'm guessing all are allowed, I would say. Because only the operand check matters, so arithmetic constant expression the left one, and is arithmetic constant expression the right one. Comparison is the same deal. So both operands needs to be arithmetic expressions. And sequenced expression. So the standard disallows comma for some reason. Right here in a constant expression, where is it? Shall not contain the comma operator. So that's okay. So sequenced expression, which on. So and oh, don't return break. So break, return false, and then check the operands. Assignment, it's not allowed. And finally, conditional. I'm guessing just check the operand. If true, if false, and the condition. Now I'm a bit confused about like, so skip one. So we also have the type constant expression, which is like size of a line of. I forgot about those. Type constant expression. They are okay. Okay. So that's arithmetic constant expression. And then an integer constant expression is just an arithmetic constant expression of integer type. This is something that we've determined earlier. Except no. Because here, so floating constants that are the median operand of cast. So this is an integer constant expression. Int 3.14. This is not an integer constant expression. int, right? Because this floating point constant is not the immediate operand of a cast, which is a bit annoying. Because I can't just reuse this function and say the result has to be an integer type. I will do that anyway and add a comment about it. So, is arithmetic constant expression and is integer type. Integer constant expressions are arithmetic constant expression of integer type, except for the following edge case, where floating points numbers have to be the immediate operand of a cast. We are not bothering to check that for now, since we don't have float anyway. So it really doesn't matter. Okay, so this is integer constant and floating point constant. Then we've got address constant. So an address constant is address constant. Is it address constant or constant expression? Address constant. So is it an address constant? And an address constant is a null pointer. That's easy. Is null pointer constant. I'm being a bit inconsistent with when I qualify stuff and when not, so let's not qualify. So if it's a null pointer constant, a pointer to an L value designating an object of static storage duration, or a pointer to a function shall be created explicitly using the unary operator on integer constant caster. Oh really, you can cast an integer, I mean it makes sense. Or implicitly. Okay, so a pointer to an L value that shall be created using unary, so the address of operation, or an integer constant cast to pointer type, or implicitly by the use of an expression of array of function type. Okay, we don't have array of function type. To do expression of array or function type are address constant. Then, so it shall be created explicitly. So if out to unary, so dryad now try cast unary expression e op. So we need to allow address unary op. Is that not a thing? Unary op. So it has to be an address, and it needs to refer something that has static storage duration. So the address of object of static storage duration. How do I check those? And has static, so has static storage duration the child operand. So it has to be like this is a function that, let's write that later. So it has to be static storage duration. And the other thing to create an address constant is to cast an integer constant to pointer type. Cast So cast expression, if we're having a cast expression where the cast type, so if you have a pointer and the operand has to be an integer constant, is integer constant expression cast child. Then we also got this case, and otherwise we return false. Okay. My language server died, so let's restart. It's address constant. So has static storage duration. So what this means is, does this expression refer to an L value with static storage duration? We already got a function like this, so let's call it is static L value. Is static L value. Is my language server dead again? I don't know why. Yeah, it's dead again. Static L value. So if you're having a static L value, if it's not an L value, then it can't be a static L value. Otherwise, it has to be an integer constant. The thing is, how do I know whether or not something is like static storage duration? Need to get like I actually have to copy this logic. Okay. So if it's a deref operation, can this then be like a pointer to an object with static storage duration? I don't. So I don't think so. I mean, let's ask like, so we want to point it to a global, like, so we want the address or something like so. Because so if this is like, so this is a potential address constant because we're taking the address of something that could be like an object with static storage duration. But I'm guessing that's not an object with static storage duration because that's a dereference. Yeah, so this is not a compile time constant. However, right, this would be. Right. Okay. So, only names can be. Now try cast identifier expression. So only a name can be an L value. Declaration. Can I query whether or not something is a global? I'm guessing. Do I have like a global decal? No, a variable decal. I'd like to know whether or not this is like refers to a global variable. And not. So I'm guessing let's add bool has, I mean, like we probably need like, yeah, bool has static storage duration. Try user attribute. I believe I can reuse 16, so we have 16 bits to spare. Has static storage duration impl. Return has static storage duration impl. And then here we are setting like here, bool has static storage duration. Set has static storage duration, has static storage duration. And then we were about setting those in the ST. Okay. ID declaration has. So this then needs to refer to a pointer, to a variable. Now try cast variable decal ID declaration. And this needs to have static storage duration. and I'm guessing like a function is also fine. So function decal is completely fine, regardless of the function. Node has kind. Function decal also has static storage duration. In all other cases, it does not. It's an extra base. Okay, let's backtrack. Where were we? We want to check address constant, right? So it's static L value, done. The other case, so we've got named constant, we don't have compound, we have those. An address constant plus or minus an integer constant expression. Okay. Let's call it is address constant with offset. So first of all, we need to have like an offset operation. So which is a binary op. Or rather like an arithmetic op. Try cast arithmetic expression E. That is the case, but the operand isn't arithmetic op add and isn't sub, then we return false. So now one operand needs to be an address constant and the other one needs to be an integer constant. So either we are having an address constant on the left and an integer constant expression on the right, or swap around, right? An address constant plus or minus an integer constant expression. And now we need to swap those. And we also need to have complete object type of the object type. So is address constant and is, let's add a helper. So is address constant for complete type. Because then we need to figure out which is so annoying. So if it isn't an address constant, then it can't be an address constant for complete type. Otherwise, we get the type. If this isn't a pointer, address constant or null pointer, we also return false. Otherwise, we get the pointee type, which means we need to split a bunch of qualifiers. So auto pointer node cast pointer type of the unqualified of the type. And then we return is complete object type pointer pointee type. Okay. And then we want to return false here. And then address constant for complete type. Address constant for complete type. And then finally, we can write this function, which is like a constant expression for, let's just say just generic is constant expression. Bool is constant expression. Which can be named arithmetic null pointer address. is named constant, or is arithmetic constant, or is null pointer constant. I'm guessing null pointer isn't an address constant. A name constant is a null pointer, a name constant or okay, I don't get that footnote. Why is it called null pointer constant here if an address constant is a null pointer, and presumably a null pointer is also a null pointer constant? So that's weird. Or is a null pointer constant not a null pointer? I mean, that could also be like a C thing, but okay. Let's just assume that this is just redundant. So is address constant, or is address constant with offset? That is a constant expression. Now one thing, which I'm guessing is not allowed, is to have something like that. Interesting. So pointer difference is not allowed in a constant expression, even though, like, yeah, I'm guessing like you have to look at the indices, which complicates things. Okay. So today I learned, I guess. Okay. So that's a constant expression. Now we need to, it doesn't compile at the moment because we need to set, when we construct a variable decal, we need to specify whether or not it has static storage duration. Which I'm guessing like somewhere in the state, we know the scope. Right, so if the current scope is global scope, so auto has static storage duration, state.current scope, state.global scope. Like so. And take another. So if we're in the global scope, then we have create a global variable with static storage duration. And then I'm guessing I've got the wrong order of arguments. No, it's before the name. I'm guessing variables are created in multiple places. Right. So not to worry, let's use that here. As static storage duration. Okay, so now it compiles, which means that we can do a check when we get set the initializer for a global variable. So let's get all the places. This is the only place. If not is constant expression. Is constant expression. The converted initializer. Yeah, var decal. So if it has static storage duration and it's not a constant expression, right? This is this clause. If it has static storage duration, the initializer shall be a constant expression. So if it has static storage duration, but it isn't, then we issue an error. State.logger.log CLOW diagnostic kind error initializer for global. Yeah, let's call it global variable. Needs to be a constant expression. So then we specify the binary annotation at the location of the decal. Yeah. And then we finish the diagnostic. Okay. And now, we don't have arrays yet. So now this one is fine, but this one is not. Initializer needs to be a constant expression. Great, that's the first half. So check initializer of global variables for constant expression. Okay, now the second half, we need to evaluate that initializer. Actually initialize that global variable. So in Loaf, we can create 3 kinds of globals. Mutable globals initialized to 0. Constant globals initialized to the specific data. And mutable global constant initialized to that specific data. So we need to evaluate that expression to get the underlying bytes that we need to initialize that. So we need to start actually like doing some form of constant evaluation at this point. And for that, we could like walk over the AST and evaluate it, but we already have an interpreter at hand anyway, right? We're generating bytecode for an interpreter. So the idea is that the initializer of a constant is an expression that we can generate bytecode for, right? All this code generates bytecode for an expression, and then we pass that to the VM to do constant evaluation. So we do constant evaluation, we get like the underlying bytes back that we want, and everything is good. So let's add an interface for that. So we want to, so we get like a vector of things. So we have a function that gives us a vector of bytes to do like constant eval of an expression. So like we do constant eval of an expression. That is the type that it's a class. So this also needs we could write this function, but then we would manually need to create a VM to do the constant evaluation. And VMs are quite expensive objects. They allocate like big amounts of memory, so it's best if somebody passes a VM to us. So if we get a VM, allow VM, so if we get like a VM for constant evaluation, right. So we get a VM and then we do evaluation and then we return the bytes. So let's implement that function. So we need to like create this constant object to get like the appropriate things in here, which requires the AST. How is that AST used? What happens if this is just null? So we get codegen function needs it. We're not calling that. What does this do? This appears to be all part of statements. So yeah, this is statement stuff. We're not calling that. We're not calling that either. We're not calling that either. And we are not in this function. Okay, so I believe we can just pass a context where the AST is null and we should be fine. So let's change this constructor to take a pointer. So if we have the AST, then we set a debug path for the module. Okay. And then we pass the address of the AST. So now we can construct the context for codegen without an AST. Then what we want to do is we want to codegen the expression in that constant. great. This doesn't. Right. We can't directly call codegen expression because it sort of like expects that we're currently inside some sort of function. So what we want is we want to like create like a temporary function, just so that we can then call. And we've got a special API for that. It's called a chunk. So allow Adam add chunk something. I'm pretty sure I have allow Adam chunk, and then we've got what's the function called? Allow Adam create chunk. Chunk allow Adam create chunk for that module. And then we build a chunk of code that produces a chunk cannot get inputs, I believe, which is a bit annoying. So hang on. How many outputs do we want to produce out of that chunk? I'm guessing we want the value of the expression. So one output. Okay. So we create a chunk that will hold the bytecode for our expression. We then push the expression onto the stack. And now what we want to do is we want to store the bytes of that expression in memory. And we want memory that persists over execution stuff, context builder. So I believe the easiest way to do that is to allocate memory to store our expression in. Allocate memory to store the expression in. So for that we call a function call built-in context builder allow lib heap alloc, and this takes the alignment and the size. So we need the type, codegen type of the expression. So we push the alignment. And we layout alignment, layout size. Then we allocate heap memory. Now heap memory is automatically freed by the VM, so we need to prevent that. Don't free, because we want to return that back to us. Don't free heap memory when we return. So call built-in context builder allow lib heap leak. It pops that, so we need to duplicate it. So we mark it as free, so it doesn't get freed when we return. So then we can return that memory from our function. Store the expression in the heap memory. Now Adam in store field context builder. The type field index 0. I'm guessing the parameters are value and address. So we've got we already pushed the value up here. Then we pushed the address of heap memory. We store that in here. And now we want to return the address of the heap memory. So I'm guessing we need to duplicate that here. So we need to do, let's actually allocate first. And then we can pick this one over and store the value. So at this point, the address is on top of the stack. Now this stack is address value, and this pick instruction then converts that into address value address we call store, which leaves the address, which we then return. Now and then build finish. So this creates the chunk of bytecode. We then execute that chunk of bytecode. We then execute that bytecode on the VM. So we create a program. Create program from chunk. Context.mod chunk. Auto success. Allow we execute that program on the VM without any inputs. We don't actually get, like, we get an address back from the, we can't use that interface. So let me first fix the include. So we create a program. We then create a process. So we need to do a convoluted API because we need to. So a lot of Adam create runtime. Need to include another header. Runtime create. No, it's in the VM. Somewhere in the VM header. Let me go there. VM start process. Process VM on the program. Okay. So we get a process because then we can do allow runtime. We can start executing that process. Runtime gets current fiber of that process without any inputs, with a single output. So that's our output. Let's just assert that we didn't panic. Constant evaluation should not panic. And then we get the, so we've got the address. We need to convert that into an actual pointer. So pointer is now runtime get. I'm guessing this is yet another header. This one we want to get a mutable pointer. Runtime get mute pointer of our process. Address type.layout. We actually need the type. So now we get a pointer. We assert that it is still valid. We have leaked heap memory, which should still be valid. We then create our result vector. Result.resize type.layout.size. We copy over. Size, and then we free a bunch of stuff. So destroy program. And no, Adam runtime destroy process. And then we can return the result. Okay. maybe I should look into some simplification API, so we don't need to do all that stuff just to get the address out of there. Oh, I'm guessing we also need to free the memory. So we get the allocator alloc.free alloc pointer type.layout.size alloc.user data. Okay, because somebody has to. Okay, but that executes a constant expression, and we get the bytes back. Definitely a lot of stuff that happens there. Especially if we already have like an integer constant literal, we're doing a bunch of stuff just to copy a number into a vector, which isn't ideal. But let's optimize that later. This is probably let's just see whether it works out. So how do we use that function when we want to initialize a global variable? So if it has an initializer, we want to, so we also need the VM here. So we want to init, what's it called, constant eval of our VM of the initializer, and then the global. Let's do it like so. Global immediately invoked lambda. So if we're having an initializer, we turn love Adam at global. I'm guessing like check whether it's const. Auto qualifiers. CLow get type qualifiers off. Type. It's const qualifiers and CLow qualified type const. So return is const love Adam at const global into our module init data layout. Otherwise we add a mutable global init data layout. We passed the VM earlier. We got the layout from codegen type, type layout. And if we don't have initializer, then we return zeroed global. We don't need to check whether it's const at this point, because we're assuming that because const variables need an initializer. Layout. Okay. Then when we call codegen, we also need a VM. So we create a VM at this point for the constant evaluation. And then we also need to destroy the VM at the end. Okay. I'm guessing we also we are leaking the module. So let's also destroy the module. Destroy module. Right. I'm not expecting this to work. Just so that we're all on the same page. Right. We panicked. Because somewhere in the chunk we're adding an invalid address. Okay, so let's figure out what's going on, what sort of code we're generating here. Well, like somewhere we dump the module. So let's temporarily dump that here. So just to figure out what the, right, we don't have mod, we have context.mod. I'm guessing we're not dumping chunks, which is annoying. Because Dan may have no idea what we're generating. I can just, let me just hack the implementation here. So chunk, chunks, chunk, chunk. So what's do we have a next pointer for chunks? We do. Chunk, chunk next. The underlying function of that chunk. Okay, now we're dumping chunks. So what we're doing is we're allocating 8 bytes, 8 aligned. We're leaking that. I think I know what the issue is. I'm pretty sure that when we call leak, we are marking it as freed, right? Which makes sense, this is right. So leak, yeah, manually marks the allocation as freed, so then we can no longer store anything in it. So we need to leak it after. So we're allocating 8 bytes. We are pushing 11, storing 11 in those 8 bytes that we've just allocated. Right here, then we're marking it as leaked, and then we're returning a pointer that contains 11. And then we don't want, right, because it's marked as freed. Because it's marked as freed, we can't get a pointer to it. Really, that's so annoying. Yeah, it's not usable. Do we have an API to get the metadata of an allocation? This one. So we can't call this. We need to get the metadata of the allocation. Allow runtime allocation alloc. Valid alloc. Allow runtime get allocation of our process. Output as address alloc. This should be a valid alloc. And then instead of pointer, we are using alloc.pointer, alloc.pointer, and then this one is the allocator, that one's the allocator, this one's the allocator. I believe we also need to destroy the module, but I'm guessing, right, we also need to destroy the module, which is unrelated, but let's do that. Hey, look at that. So we've got our chunk, we've got a global that is initialized with some bytes, and it prints 11. Excellent. So we don't need to do the debug print. So we just got a global that is initialized. So we've implemented like compile time evaluation at this point. by essentially interpreting things twice, which is really cool. Okay, let's print that. Implement compile time evaluation of global variable initializers. Now, still got a bit of time left. We can now very easily add constexpr, because a constexpr variable is just a named constant that we can use in such an initializer. So we need to pass, I'm guessing, some sort of storage specifier. Storage specifier constexpr, which is passed. So where does it say constexpr? No, it's constexpr, but right, it's implicitly const. This is a broken reference because we are using a draft of the standard. It's a constant expression. I'm guessing the initializer has to be a constant expression. Yeah, but it's been set in a different. So storage class specifiers, we pass them part of these specifiers. So what we want to do. So first of all, we want to store metadata of our variable declare. So we've got the static storage duration. Let's add like various flags for our variable. I'm guessing like do constexpr variables. I'm guessing like you can have a static constexpr, so there are thought. Okay, so let's add flags. Flags which are unit 16. So we've got has static storage duration. We've got is constexpr. Flags. Set flags. Impl. Unit 16 flags. Bool. Let's call it flag. Flags, which returns flag, which returns flag impl. Flags. Has static storage duration. So of course flag and variable declare has static storage duration. It's not 0. Right. Same deal. Flags. Variable declare has static storage duration. It's non-zero. It just happens to work because the constructor is not typed. Because we're passing an int and a boolean is an int, which is a bit annoying. Variable declare right here. Var flags. Static storage duration, otherwise 0. Var flags. Var flags. Oh, and then of course, really important. Let's call it no flags. Just so we have no flags. Okay, we want to add constexpr. So bit of like type specifier list. Where is this one used? Yeah, let's just call it decal specifier list. Yeah. And in addition to that, I also want to get like storage class specifier. So I'm guessing I need to add like storage class specifier somewhere in here. Storage class specifier. So we've got constexpr. Type specifiers. So we also got type qualifiers, and we've got storage. Is it storage or storage class specifier? Storage class specifiers. Class specifiers. It's a symbol table of storage class specifiers where we are mapping constexpr to CLO storage class specifier constexpr. Great. We then want to reserve that one. Storage class specifiers, and when we are passing the decal specifiers, we also want to allow storage class specifiers. Right. So then we want to get an even uglier type, storage class specifier, and this returns type specifier pair, which is a type, and storage class specifier type specifier pair. I'm guessing the specifier can be optional. This is so nicely formatted. Thank you, Clang Format. Does this help? A bit, yes. And then we also add an optional storage class specifier, storage class. If we are holding a type specifier, else if holds alternative CLO qualifier type. Qualifier T or specifier or qualifier. Otherwise, storage class gets CLO. Storage class specifier or qualifier. If we already have a value, we log an error because we can only have one specifier at a time, which isn't true. You can have static and constexpr, but okay. Let's refactor that when we get there. New storage class. New storage class. And then here at the very end, we're returning a type to result type. Okay, and this really needs to be refactored, but I'm not bothering to do that right now. And then we are returning a type specifier pair consisting of the result type and the storage class. Let's then rename that to let's rename that to type web storage class. And Okay. So our type we have storage class. You need a lambda. I'm guessing. All right. This one is a type of storage class. Okay. So now we're getting a type of storage class, which means that when we pass a parameter decal, we are getting not a base type, but a type of storage class. How do I call it? Type store dot type. If type store dot specifier has value, we issue an error, invalid use of storage class specifier on parameter declaration. And then in the other case where we're passing a declaration, we're also getting like type of storage class type store, type store dot type. If type store dot specifier is CLOW storage class specifier constexpr, then var flags gets CLOW variable decal is constexpr. And then I also need to type state.as. Types.build. So we also need to add const to the type. For that we need to create a copy of our type. And then we need to create qualified type const const, and then I'm guessing the base type. Right. So we got that, and then you've got wait, what does this one? Oh, right. Same deal here. So we also get like the type of storage. Type of storage. Type of storage. Let's just check whether that compiles. It does not. We are missing something. Right, type name in parents. We want the I'm guessing there was some other kind. Specifier list. Qualifier. We only have a type qualifier list. So you pass a thing, and then you don't get a base type. You also get like a type of storage class. Type store. Type store. Type. I mean, I need the type earlier. Need it up here. And then we need to also don't have a type specifier at this point. So we go to the parameter decal and copy that error message. This one. Invalid use of class specifier in cast. Size of liner. I'm guessing we've got, do we get like a location at this point? We do not. So let's get a location. Here. And then we need to specify that we want a const of type. And that compile does not compile. Why do you not compile? What exactly is decal type? Right. Type door. Type store. So we want the type here. So we're parsing. Let's see what happens when we add a constexpr variable. We don't want one, apparently. So we're parsing a global declaration, which parses a decal specifier list, which parses a list of type specifiers, type qualifiers, and storage class specifiers. So why are you not parsing constexpr? Then you're passing like an init declarator list, which consists of an init declarator, which consists of a declarator. All right, I'm guessing we're missing like why? Why passing global declaration? That's really odd. Yeah, that apparently doesn't like constexpr. You still want const, right? You're fine with const, but like, there's no difference between the. Oh, yes, there is. We've got like some maximum munch issue here. We need to pass constexpr first because it's a prefix of the other one. Right. But so DSL symbol. All right, now you need this one. You only need one. Now you need two. Okay, like so. Right. That we don't have constexpr. Okay. So we're passing constexpr, and we've already seen that it made this one const, which is great. Now the second part is other global. This should also be allowed. It definitely shouldn't. This shouldn't happen. I'm guessing because this right, we need to get the unqualified type. So check it the unqualified type and proceed further. Right. Initializer for global variable needs to be a constant expression, which you can now easily adjust because we now can define name constant to check ID. I'm pretty sure, like, we're checking this. I have similar code somewhere. I believe it's static L value. Code like this. We can copy for is named constant. And in this case, we don't want to have static storage duration. We want is constexpr. Great. Except we are failing somewhere in here. Yeah, but like the identifier expression, like what else is the expression declaration supposed to be? So we've got an identifier expression like for global. Why are we hitting this code? Oh, because... Oh, right. I know why we're hitting this code. We are hitting this code because when we do code gen for constant eval, we also need to add all constexpr global variables in here. So we're somewhere in here, we're evaluating the expression, but it doesn't know about the global that we're referring to in the thing. So we're doing something really ugly because like the stream's getting long. We delegate that to next stream, and instead, so we need to like now evaluate the. We need to get the value of global to compute the value of other global. But this isn't something that is available to us unless we already initialized global. So we need to like sort of recursively initialize the other global first. And so yeah, we need to figure something out. It's not trivial because we also can like, we can't have cycles because C goes from top to bottom, but we need to figure that out, which global we then need to initialize and so on. So it's an entire deal. Instead, let's just add, I believe currently this one should be fine, right? But we need to check that because this is an error because this isn't constexpr. So let's check that and end the stream. So when we create like somewhere not in here. So a variable declare. So if we are creating a variable declare, when we initialize it right here. So if we have static storage duration or constexpr 1. Then we need to initialize it with the constant expression. Right. So we have the ability to constant initialize stuff, but we already have constexpr. What we do not have is the ability for constexpr to refer to other constexpr. This one works at this point because, but this isn't initialized at compile time. This is initialized at runtime. And yeah, but as you can see, like the global, this is initialized. Okay, so add support for constexpr specifier. So in a way, the constexpr specifier at the moment, all it enables is the ability to mark a non-global variable as having a static initializer. But that's all I have time for today. So thanks for everybody who stopped by, and until Thursday, when we will continue working. Oh, I can't stream on Thursday, so until next week, when we will implement like proper constexpr dependencies properly. Thank you.